Hello, we are Group 10, WHY. WHY is the abbreviation of our group number's name. And before our introduction, let us see a video clip about Da Vinci clock. This clock is based on a sketch from Leonardo da Vinci. The mechanical principle used in his clock are still used in modern mechanical clocks and watches. A mechanical clock is a complex machine made up of simple components working together to keep time. The power of the clock is provided by a hang weight. When the drive wheel is wound, it raises the weight to store potential energy. This energy is used to move the gears in the wheel chain. A rigid wheel allows the weight to be wheeled while the rest of the gear chain is locked. The energy stored in the drive wheel needs to be released in a controlled manner or else it will be released all at once. Escapement provides that control the escapement acts like a switch to meter or release of stored energy through the escape wheel. As the escape wheel turns, it comes into contact with the pellet teeth of the escapement, which stop the forward rotation of the escape wheel. This is done in synchronization with the movement of the pendulum, which in this clock is attached to the escapement by the shaft. The rate of the escape wheel turns is controlled by the pendulum. The length of the pendulum determines the rate at which the pendulum swings back and forth. The escapement also provides energy to the pendulum to keep it swinging. The escapement must have proper clearance so that the teeth of the escape will advance one at a time instead of uncontrollably or binding against the pellets and stop the escapement on swinging. Why we show the video clip? Because we are inspired by the idea of Da Vinci clock. Now, let us talk about WHY's own Da Vinci clock. We inspired by Da Vinci clock, then use the concept of a Da Vinci clock and do our simplified version of it. We had considered buying ready-made components or 3D printing and using Blender with Python code. However, due to the limited time and other reasons, we eventually found out a great way to make the practical clock, making it by Lego bricks. Therefore, we can test more variables for our design. What does it do? It's a clock, so we all know that it uses to measure a period of time. Why we choose it? Originally, we didn't have many ideas about the clock, so we Googled for more information and found Da Vinci clock. There are two types of Da Vinci clocks, and we selected the one that is more interesting to us. Then we discussed for how we can test it in more and in our own version. Finally, we decided to use Lego bricks because we can arbitrarily change the structure of the clock. In our own version, we remove the gears of the Da Vinci clock and focus on testing the rotation speed of the twin wheels. Lego bricks are convenient to us to assemble our model because we can change the model as well.
I'm going to talk about the math for our project. In the midterm presentation, we already showed that the potential energy E is equal to the product of M, G, and H. and the kinetic energy K is equal to 1/2 of I omega squared. For our design, the rotational inertia is 1/2 of m ball L squared. So in this case, the kinetic energy will become m ball L squared omega squared divided by 4. Now consider our design. We'll see that the angular velocity will be 1/3 of pi divided by delta t, and delta t is the interval of time for the gear to move one tooth forward. Since the angle between two rods on the pendulum is designed to be 120 degrees, so when the gear rotates by one tooth, the pendulum rotates 1/3 of pi. If we don't take energy loss into consideration, that is, the potential energy is all transformed into rotational energy for the pendulum, we can write out the equation E equals to K, which means mg delta H equals to m ball L squared times the square of angular velocity divided by 4. And after some calculation, we'll get the result of delta t equals to pi L over 6 times the square root of m ball over mgh. By changing the variables of m ball, and L, we'll get different time interval for our design, where m is the hanging weight and m ball is the weight we added to the end of the pendulum, which we use Lego people in our design. L is the interval of pendulum. In our project, it's about 14 Lego units. Next, we'll move on to the Python simulation for our design. Here is our Python simulation. The first part is the equations we use in this project, and we showed it in the math part. The second part is the setup for this Python project. The first cell is some variables we use, like pi is for pi and g for gravity. Lmax is the maximum interval of the pendulum. B is the spacing of Lego brick. It's very close to one Lego unit, but not exactly the same. And H is the falling height per time. N is the hanging weight we added to the string, and we use half of the Lego person. And M ball is the weight we added to the end of the pendulum, which we use a Lego person. So these two values, I get it from a Lego wiki or some website that they have a list of the weight of every brick. For convenience, I set all the values to be in SIE. And here is the function for the equation delta t equals to pi L over 6 times square root of m ball over mg delta h. And delta h is h. Right? set up here. So then in the parameter list is in level unit, which means when we input the maximum value 7, we'll get Lmax here. That is the maximum interval of the pendulum. And the next part are some graphs that shows the relationship between each variable and the time interval. The first graph, we want to see the relationship with the length of pendulum and time. So we set the number of end ball and the number of hanging weights to 1. And in the graph, we can see that as we in length the interval of pendulum, the time will increase. And the second graph, we want to see the relationship between the weight we added to the ends of the pendulum. So we set the length to be maximum and the hanging weight to be 1. In the graph, we'll see that the more number of balls we added to the pendulum, the longer the time interval will be. And the third graph, we want to see the relationship of hanging weight and time. So we set length to be maximum length and the weight on the pendulum to be 1. The graph shows us that if the hanging weight is heavier, then the interval of time is shorter. And the last part, I made a simple interactive widget to tag more values. So let me run this code first. Okay. So I want to see the maximum time interval we can get from the design is 0.2634 blah blah blah, and the minimum time interval we can get is 0.0209. Our goal is to make our clock 1 second for 1 round of the chair. So ideally, we'll want the time interval to be 0.1667. And we're playing around with the variable. This is 0.1578. That is for the Python simulation.
After several tests, we couldn't make our clock move. The process only went success to the weight dropping step. We discussed and had some conclusions. First, the angle between legs we put on the bottom of rotary pendulum. Because this component is not fixed, so the angle might increase during pendulum rotating. Thus, the legs will just stuck in the teeth of gear. Second, the movable rotary gears. Since we have to make the axis of gear rotatable, we could not fix it. However, while this axis rotates, it would move horizontally. That made one of the legs at the bottom of pendulum couldn't push its corresponding teeth. Hence, the clock stopped moving. Third, the upper part of pendulum. Because we haven't adjusted the height to proper place, we didn't make it fixed. This led to the consequence that bottom of it also moved, which means the legs stood a high chance to push their teeth. And last but not least, the line between pulley and axis. This line would tight easily during dropping the weight. For the front part, we have finished the basic structure of our clock, and several uncertainties made it inoperable. We moved on to the next step: fix the upper part of pendulum and add bearings and add loads onto it. It was difficult to decide how high we should fix it, because we have to make sure legs on the lower part of pendulum could match the teeth. After that, we put our loads, these Lego characters, onto the upper part, but I still failed to synchronize the whole clock. The legs and the teeth would move together at first, and then the axis moved separately, or legs were not able to push the teeth. Okay. Go. Take 3. Yay. Yay.